Warning: iodine and potassium iodate are oxidizing. Iodine vapor is toxic. Wear gloves and masks when handling them. Hi, here is MIH. So recently I have been exploring some color changing reactions and I wanted to recreate the oscillating iodine clock reaction. For this, I need potassium iodate. The industrial method of manufacturing it is reacting molten potassium chlorate with iodine to produce potassium iodate and chlorine. In the lab, adding iodine to potassium hydroxide can yield potassium iodate conveniently. However, I wanted to try another method which involves hydrogen peroxide. Mixing a solution of acidified hydrogen peroxide with iodine would give clean iodic acid at high yields, and adding potassium carbonate to it would produce potassium iodate. We start by weighing 7.62 grams of elemental iodine in a mortar. Iodine is a shiny purple-black solid that readily sublimates at room temperature. For this reason, do this step fast and minimize exposure to iodine. You can see that the mortar was already tanned yellow by the iodine vapor. Next, the iodine is grinded into a powder using a pestle. I ended up not grinding it very fine because I want to be done as soon as possible. However, looking back, a fine powder will increase the reaction rate by a lot later on. I scraped the iodine off the mortar and scooped them in a 100 milliliter conical flask. Try to transfer as much of the iodine as possible since, well, it is not cheap. To the iodine, about 10 milliliters of hydrochloric acid is added. The exact amount and concentration isn't important, and using other acids like sulfuric and nitric acid will also work. The mixture is then heated above the alcohol lamp until purple iodine vapors are visible. At this point, measure out 50 milliliters of 7.5% hydrogen peroxide and gradually add it in. Here I used a separatory funnel, but it is completely unnecessary. Continue heating the flask and swirl it gently to mix the reactants. To reduce evaporative losses of iodine, I placed a watch glass on top. What happened next hit me completely off guard. I went away to grab some equipment, and then when I came back, I saw this horrific scene. The mixture boiled violently, and lots of iodine vapors spray out of the flask. I retreated backwards, and after a few seconds, the mixture seems to stabilize a little. No more vapors are forming anymore, and the solution stopped boiling. I let out a deep breath. The whole room now was full of iodine vapor, so I left the room for 30 minutes. When I came back, the color of the solution turned from orange to yellow. A lot of iodine disappeared, and only a few large chunks are left behind. I added the rest of the hydrogen peroxide, and a lot of bubbling occurred. There are also quite a bit of iodine stuck on the walls of the flask. In this reaction, hydrogen peroxide oxidizes the iodine to iodic acid. Hydrogen peroxide only has a strong enough oxidizing power in acidic environments, which is why I added the initial amount of hydrochloric acid. However, the iodic acid generated is also a strong acid, and so the reaction can catalyze itself repeatedly. This is called a self-catalyzing reaction. Other examples of this include the reaction between oxalic acid and acidified potassium permanganate. The manganese ions produced will catalyze the reaction and make it go faster. A few minutes later, the bubbling settled down a bit and the color of the solution turned to a pale yellow. This is because most of the iodine in the solution is consumed. I checked the pH and it was about 2, indicating that a strong acid is present like iodic acid. When the bubbling seems to stop and the solution darkening again, I measured out another 50 milliliters of hydrogen peroxide and slowly added it in. The color of the solution quickly faded to yellow, and I checked the pH again, yielding similar results. More peroxide is added in, and I shook the flask to get down the iodine that stuck to the glass. I then carefully transferred a portion of the solution to the mortar I used earlier. This step will hopefully take up all the iodine stuck on the mortar and minimize the waste. I gave the solution a good stir and let it settle. After a few minutes, I transferred everything to a larger conical flask. At this point, there are still a lot of floating iodine chunks in the mixture, so I came up with the idea to add some diethyl ether to the flask. I added about 15 milliliters of diethyl ether, and the solution immediately darkened. I increased the stirring speed, and the color of the solution turned orange, and then red. The iodine cannot dissolve well in water, but it readily dissolves in the diethyl ether. The ether then extracts the iodine from the water phase into the organic phase. When the stirring is stopped and the solution settled, you can clearly see a dark red layer of diethyl ether floating on top. Most of the iodine has dissolved in it, and the color of the water phase became a lot lighter. I then added some more hydrogen peroxide and continued to stir the mixture. When the iodine reacts with hydrogen peroxide in water, it has a relatively small surface area. But when the iodine dissolves in diethyl ether, a large surface area can be achieved by vigorous stirring and letting the two layers mix. This, in turn, made the reaction go a lot faster. Looking back, I should have dissolved all the iodine in ether first, and then add the hydrochloric acid and hydrogen peroxide. That would certainly resulted in an even better yield and a faster reaction. Here is the mixture 10 minutes later, and the color visibly lightened to a pale orange. When the stirring is stopped, the ether layer was a lot lighter than before, which tells me that most of the iodine in it had reacted with the peroxide and transferred to the water phase. I let the mixture stir overnight, and here is what it looks like on the next day. The solution turned completely colorless except for a little bit of unreacted iodine sitting on the bottom. The ether layer cannot be seen anymore because it was also colorless. I then transferred the supernatant to another beaker and left the iodine chunks behind. Here the solution is slightly tinted yellow since some of the iodine dissolved in the water again. I poured another 50 milliliters of diethyl ether in the flask to take up the remaining iodine. The mixture is then moved to a small beaker, and I stirred the solution vigorously to transfer all the iodine to the ether. After the extraction, the ether layer was completely dark and opaque. All the contents of the small beaker is then poured into the large beaker, and I stirred everything again to let it react. A while later, the color of the iodine did not completely fade, but I am running out of time, so I proceeded to the next step. About 5 grams of anhydrous potassium carbonate was measured out and dissolved in about 10 milliliters of water. I used the same beaker from the extraction step, so the remaining iodine can be recycled. The mixture is stirred to let all the salt dissolve, and then heated gently above the alcohol lamp. The brown iodine at the bottom of the beaker slowly separates out into the solution, and eventually fades away completely. The iodine reacts with the potassium carbonate to produce potassium iodide, potassium iodate, and carbon dioxide. This allows us to recycle the iodine completely by dissolving it in the water. Next, add the potassium carbonate solution into the large beaker slowly. A lot of bubbles form. The potassium carbonate reacts with the iodic acid in solution to produce potassium iodate and carbon dioxide. In a closer shot, you can clearly see the bubbles forming on the surface. After all the potassium carbonate is added in, the color of the solution darkened. I did not expect this at all, because the potassium carbonate is supposed to remove the remaining iodine colors and turn the solution colorless. However, when the solution is stirred, the water layer slowly turns from dark orange to light yellow. I found the process quite beautiful when looking down from the top. The purple-red spiral of iodine slowly fades and disappears in the lower water layer. I then increased the stirring speed, and the spiral was destroyed in the water. The solution turned orange, but only 1 minute later, the color visibly fades. This tells me that most of the iodine left is destroyed by the carbonate. After a few minutes, I checked the pH of the solution, and it was around neutral. Looking back, I should have added some more potassium carbonate and bring the pH to about 9 to remove all the residual iodine. After most of the color disappeared, I stopped the stirring and allowed the solution to crystallize. I poured all the solution to 2 plastic petri dishes, and I left it on the table for a week. After the week, a decent number of white crystals appeared in the dish. They resemble sodium chloride crystals to some degree, since they are rather cubic in shape instead of the needle-shaped crystals of other salts. I decanted the rest of the solution into a small beaker. You can see that it was slightly yellow, probably due to the remaining iodine. At least, it is quite fortunate that the impurity did not contaminate the crystals, as the crystals are perfectly white. I boiled down the solution to about 10 milliliters and let it cool on the table. As it cools, white crystals slowly separate out. Please forgive the bad pixel qualities since I didn't bring my camera this week, so I have to use my phone to take footages. When the solution cools to room temperature, a large amount of crystals crashed out. I didn't want this to happen at all, since this makes it nearly impossible to separate the crystals and the mother liquor. After trying to separate the crystals out, I gave up and discarded it. A much better idea is to decant the mother liquor when it is still warm to limit the amount of crystals forming. My crystals in the petri dish are already quite dry, so I scraped them off using a spatula and transferred them to a vial for storage. This is quite a messy process, since the crystals are very small and easy to spill out. You can see from the video that I spilled some all around the table. In the end, my yield of potassium iodate is 6.33 grams, which represents a percentage yield of 49.3%. It was actually not super bad yield, since I lost some of the initial iodine as vapors, and a huge amount of the remaining iodate is in the crystallization liquor. However, I wanted my potassium iodate to be as clean as possible, since it will be used for the iodine clock reactions, and small amounts of impurities would significantly impact the reaction. I got all my supplies for the iodine clock, and I have already did a test run in my school, which turned out to be very successful. So I think I will do the reaction along with some other oscillating reactions in the near future. See ya next time!